concept of real-time video processing started in the year 1960s and 1970s with the development of digital image processing. With the development of computers and microprocessors in the year 1980s, it made the real-time video processing possible. Before we learn how video processing works, let's talk about what video is. A video is a sequence of image or frames displayed in a succession to create the illusions of motion. These frames are displayed at a certain rate known as frame rate, which is typically around 24 to 60 frames per second for most videos. Here is the example of video with different frame rate. Now let's talk about video processing in real time. First of all, what is an image filter? An image filter may mean many things. The type of image filter that enhance image to make video falls into three groups. The first type is traditional image filter, which manipulate image without adding any additional information such as blurring, sharpening, and tone mapping filters. The second type is the algorithm that do all sorts of tricks like giving you puppy ears and nice goggles like I used to have, or a fancy beard. This type typically makes use of computer vision techniques like face landmark detection. Third type is neutral filters, which can transfer cycle between images, manipulate properties of image, colorize, grayscale image, and so on. As their name suggests, neutral filter use neutral words to do all those cool stuffs. How can you transmit huge data over the air in real time? The answer is video compression. You might have heard of codec. A codec is a piece of software that encodes and decodes data. The encoding part compresses the data, making it easier to store and transmit. In the decoding part reverses this process, recreating the original data as closely as possible. If codec is not limited to video, they can be used to encode and decode many types of signals. But for now, let's focus on how video codec works. Firstly, let's talk about how still images are compressed. In short, images are compressed by throwing out the information that is less visible to human eye and storing redundant data more efficiently. We can easily extend image compression to video compression by compressing a video frame by frame. This approach is called spatial or inner frame coating. Even doing that alone would significantly reduce the file size. In a typical video, many consecutive frames tend to be nearly identical. We can make use of this temporal inner frame redundancy to further compress a video. First, let's think of an extreme case where nothing moves in a video. Instead of storing each one of these identical frames, we can simply tell our encoder to keep the first frame and repeat n times. That would save us a lot of space. Now let's think of a more realistic case where only some part in the video don't change. This time we can do the same thing but more locally by dividing the frames into blocks and repeating only the blocks that don't change. What if all the blocks change between consecutive frames, but some change a lot and some change a little? Instead of checking whether a block has changed or not, we can search for a given block in the next frame within the neighborhood. This process is called block motion estimation. Object detection and object recognition are related techniques in computer vision, but they differ in execution. Object detection involves locating instances of objects within images, often using deep learning. It's a subset of object recognition where objects are not only identified but also located, enabling the detections of multiple objects within the same image. Object recognition employs various approaches, with machine learning and deep learning gaining popularity. These techniques enable recognition of objects within image, addressing object recognition problem effectively. There are two approaches to performing object recognition using deep learning. 1. Training a model from scratch. Training a deep network from scratch involves collecting a sizable labeled dataset and designing a network architecture to learn features and construct the model, though requiring substantial training data and manual setup of CNN layers and weights. 2. Using a pre-trained deep learning model. Most deep learning applications use the transfer learning approach, a process that involves fine-tuning a pre-trained model. This method is less time consuming and can provide a fast outcome because the model has already been trained on thousands or millions of images. Machine learning techniques are also popular for object recognition and offer different approaches than deep learning. Common examples of machine learning techniques are HOG feature extracting with an SVM machine learning model, back of words model with features such as SURF and MSER, the Euler-Jones algorithm, which can be used to recognize varieties of objects, including faces and upper bodies. Challenges. In real-time video processing, there are many challenges we face. Some of the key challenges we encounter during real-time video processing are latency. It is the delay between capturing or generating video data. High latency can make real-time applications ineffective, especially in critical situations like live streaming or autonomous driving. Processing power. Real-time video processing requires substantial computing power to handle large amounts of data quickly. Maintaining high performance is challenging without overheating or consuming too much energy, even with advanced GPUs and specialized processors. High bandwidth. Transmitting real-time high-resolution video data requires a lot of bandwidth. Managing bandwidth effectively is crucial to prevent bottlenecks and ensure smooth transmission, vital for applications like live streaming. Complex algorithms. The algorithms for tasks like object detection, motion estimations, and video stabilizations are often very complex. Potential future work. The future of real-time video processing holds exciting potential for advancement across various domains like advanced AI for quick, precise analysis. In near future, AI algorithms will become faster and more accurate, enabling applications like rapid decision making and robotics and autonomous cars. Real-time video processing with AI will revolutionize various sectors such as smart cities for automatic traffic light adjustments and optimized waste management, healthcare for early diagnosis and improved elderly care, retail from tracking customers' behavior and targeted promotions. There are many other future works of real-time video processing